Good morning, everyone. I'm Sam Motoshi, coming from the University of Tokyo. This is the second day of the symposium. We have totally 11 brilliant speakers in the symposium till the 8 o'clock in the evening. Please enjoy the talk and discussion. And the first talk will be given by Shin'ya Nishida, who is the leader of this innovative area of Shitsukan project and the main host of this symposium. Probably no need of introduction, I think. And then please start the talk. The title will be Image Futures for Human Shitsukan Perception.
Thank you very much. Okay, so I'm leading one of the group of this project, and in our group we are running a variety of issues, including visual Shitsukan perception, combined with the psychophysics and modeling. And the other is visual Shitsukan and the media technologies. And the third one is Shitsukan science and neurology. And the other is tactile Shitsukan perception and psychophysics. And the last one is auditory Shitsukan and psychophysics and modeling. And since I have little time to explain these issues, so most of these studies are shown in the poster session. So please see these studies. And today I'm concentrating on this aspect. And but before that, I just quickly say something about the technological issues. And this is one example that we call the deformation lamp. And this is a projection mapping technique that you can make real object appear to move. And the other thing is this is a hidden stereo. And this is an extension of the concept of the Hengen-To or deformation lamp. And the point of this technique is that you in a real 3D displays, and normally you have to wear glasses to see 3D, of course. And our technique also needs stereo glasses to see 3D. But the critical difference is the standard 3D display. If you take out your glasses, and then normally you see a blurred image because the left and right images they slightly shifted each other so that the image mixed up and make image blur. But our technique is to try to hide those components, and without glasses you see completely the clear 2D images. So this is we cheat the human stereo optic system to generate the disparity, and then the binocular fused image is as good as the original one. Okay, so this is a kind of technological study we've done, but today I'm focusing more on the psychophysical aspect of human visual perception. And originally I'm interested in the material perception in 1990s, and it's an age where the computer graphics is advanced, and even in commercial movies we can enjoy the realistic images very by computer graphics. But the problem is that we learned that in order to generate the images, you need a very complicated computation to simulate the physical world. But the question is, why those images look nice and realistic to humans? And because it's merely impossible to check for the human brain to check the detail of the physical correctness of the image. But still, it's important for the correct physical simulation to generate the image. So what's happened? And so the general framework proposed, for example, by David Marr is that this kind of framework that this is a physical variable, and this is what happened in the world, and this is a proximal stimuli on the retina, and you get some perception. And basically, there is the process to generate the retinal image from the outer world is optics, forward optics. So that what the visual system has to do is a kind of inverse optics to estimate the physical variables from the images. But in case of a material situation, this is a combination of the geometry, material, and the lighting, and then you get images. And so this is optics process. Sorry, the direction is opposite from the last slide. And the inverse optics is like this. But since the BLDF that we learned a lot yesterday is so complicated, and the dimension is very high, and also it's very important to have a realistic environmental global illumination to generate a realistic image. But that means that in the illumination also is very, very complicated. So that it is incredibly complicated ill-posed problem. And in order to solve it, we need to assume a number of assumptions about it. So the more realistic framework is to use not precisely to solve the inverse problem, but just looking at the more weak statistical correlations, and based on those correlations, estimate somehow statistically what happened in the world. And so in particular, what's important is modulation, statistical modulation of the image, not the image itself, but how the image statistics are modulated by the reflectance, for example. And in this case, the image is, this chrome. It has a very clear, sharp specular component, but if it is seen through this and then cut it, you see more blurred object. But what is important is what is what exactly reflected in the image, but how this image are modulated. And since you know what the world is like, so that you know some image statistics of the world, so that from this image you can infer how the natural image are modulated, and then you can get some inference. So this is the whole study and done by mainly by Botelson and Ted Ellison, and they show that we show that the image statistics like luminance histogram, in particular its skewness, is the critical features to predict grossness. And now, and also that you have heard this yesterday as well, but Sawayama-san have found that not only the grossness perception, but for example the wetness is affected a lot. In this case, not only the luminance histogram modulation, but also the enhancement of color saturation is critical. So in this case, you see it more wet-like, and so. I explained this study because this is a kind of template or a study where what we should do to prove that the specific image features are actually the important features of the human visual system. The first, it's a perceptually. If you apply this transform, then we get rating. Actually, the most of the images we obtain the clear. Most of them think that image looks wet. That's one point. And also we have to understand the physics and why physically this should happen. And as we heard from Imari-san, for example, yesterday, that there are a variety of physical reasons that the increase in the number of the reflection within the object produced by wetting will make a sharpening of a spectrum or enhancement of the color saturation. And also, this is should be tested physically. And Sawayama-san measured a variety of chromaticity of the variety of objects. And actually, he found that the same object is when it is wet. The chromaticity, the saturation is about 1.43 times higher than the dry object. And also we need to know that under some situations, the effect is very good, like these images. But in the other cases, the same operation doesn't work well. So that we have to understand the reason. And and we found that the critical parameter is the entropy, in particular the hue entropy. That means that how many different colors exist in the image. And in this case, there are many colors here, but this is only 2 colors. So that in order to get the wetting process, wet transform work well, you need a variety of colors. Why? So that the logic is like that because when you consider the real world, sorry, and when you make it wet, you can change the luminance histogram and also the color saturation. But in the real world, you have a variety of objects that have these properties, like this post. This is very glossy color, very colorful thing. So that in wetting process, what is likely happen is that this process occurs at the same time. So that means that if there is wetting occurs, then everything around in that field are affected in the similar way. So that means that the more colors there are, the more evidence that it is likely to be wetting. And if it is actually the original genuine property of the surface, then probably the color saturation change is only occurs for the limited portion of the image. So that this is the critical thing. And another example is this is a fineness thing, and the point is that this is originally motivated by the computer graphics literature. That here you see that this is the fine hairs, and this is the in this case here is rendered with the 1 pixel with this, and this is the 0.3 pixel with this. And although the image can be shown only at this pixel level, you need to render the original image at the higher resolution. The reason is that probably related to this. And here you see the textures, and probably from here to here you see this one is finer than this. But actually there is no physical change in line width from this line. And from here to here, nothing changed. With regard to the width, nothing changed. And what actually happened is the reduction of the contrast. And in this case, you think this is finer because we just reduce the contrast of the image. The reason is that this is more physical thing, and this is coming from the central limit theorem. And in a random process like hairs, you samples a lot of random black and white pattern within the single pixel. And if you make this one finer and finer, what happens is that you don't change the mean luminance, but also the variance of the intensity across different points reduce. And also, we assume it becomes more like a Gaussian. This is a simple central limit theorem, and so that this can predict that why the reduction of contrast is related to the fineness. And the important point is that human visual system is actually sensitive to it. And another interesting thing is that, as theory predicted, the distribution of the luminance histogram is important because we change the luminance histogram of the images, and just like this unimodal, Gaussian-like situation, we actually obtain the strong effects of a contrast on the fineness. So that this is theoretically predicted. So that this framework, we think that we can understand how the visual system works. And also we can understand what is necessary to prove that an image feature is the perceptual Q of a material properties or other perceptual properties. And one is that there should be the physical link, and also we have to measure it physically. So I'm saying that using a machine learning technique or a deep learning technique, you can accidentally find that some features are actually related to your perception. But without this kind of evidence, it could be very spurious correlation. So that it's important to find this kind of physical reason why it works. And also that we need not only the correlation, but also the causal relationship. So that we need to change that parameter, actually change the perception itself. Otherwise, we cannot prove that is actually working. It is just a spurious correlation. And also, we need to understand that in most of the case, no Qs are sufficient to explain everything. And for example, the size of the object is a strong Q of the depth, for example. But the size itself is not uniquely define the depth. So that in order for specific features works as a Q, and then you need some context, and you need to understand what kind of context is necessary. So that the effect condition for example, gross the wetness perception is a hue entropy, and the sub-resolution fineness case, it should be the random fine texture with a unimodal luminance histogram, and so on. And, but this situation is a little bit complicated for gloss case, because in the case of gloss, luminance histogram works, but the condition under which this works is a little bit complicated, and so many people complain that the shape features are important, so that the luminance histogram is not sufficient, of course. But the important observation here is that if you change the luminance histogram, you have different impression about the material. But the shape perception is relatively stable, and this is related to the yesterday's boxing sheath talk. That in general, the material change doesn't affect our shape perception, and the luminance histogram change actually affects the material, but not shape. And we actually found that what is critical is the luminance order of the image, gradient order of the information. And because the luminance histogram matching doesn't change the luminance order of the information, of the luminance gradient. So that we did, in particular, Sawayama-san did a lot of study showing that it is critical for the visual system not to change the luminance order to see the same shape. So that, in other words, as long as you only change the tone curve without changing the order, shape of the object remains relatively the same. So that in a sense, this is a kind of invariant thing. So that we believe that this is an example that the asperity material like velvet case. Sometimes this kind of situation occurs. This is naturally occurs. Sorry for not clearly visible, but important point is that these specific materials, under some illumination condition, luminance order is changed, and in that case, the subject perception is actually affected by this manipulation. That means that even when it's physically realistic, our shape perception is affected. So we currently have a simple idea that we use the two kinds of information in different way. One is the luminance order information, and or the direction of the intensity gradient information. That is mainly related to the shape. But gradient magnitude information is related to the material, and this is related to the BRDF component. So probably we need to consider how these components are separated process. And but there are a variety of remaining problems, and one is how complex are human Shitsukan features. For the image features, for example. The luminance histogram is a very simple statistics, or a little bit complicated thing is the marginal statistics of V1 statistics or Gabor statistics. And a little bit more complicated is the V2 statistics of Portilla Simoncelli, or the more higher level deep convolutional features. In relation to that one, for example, the mid-level perceptual features have been proposed from the Bart Anderson's group. And they show that the highlight perception, grossest perception is related with the perceived coverage or contrast and the sharpness of the highlight. But yeah, that's fine. But they show that by asking the subject directly judge these parameters. So it's not image computable. So we want some features that is directly image computable. And for the Portilla Simoncelli statistics. We found a long time ago that when we, for example, in these two images, this is a highlight and this is also highlight but shifted. So that this is the kind of stimulus used to show that the spatial structure is important to see the gross highlight perception. And this looks glossy, and this doesn't look glossy. But if you apply the Portilla Simoncelli texture synthesis and compare the resulting images, there's little difference. That means that these differences cannot be captured by the statistics represented in the Portilla Simoncelli model. So that means the B2 statistics. It's a joint statistics of the spatial frequency and orientation and so on. But interestingly, the recent development in the deep learning, it have been applied to the texture synthesis context, and initial attempts have been applied to this kind of image, and PS statistics doesn't work, as we showed, and then this highlight structure cannot be recovered. But in the convolutional tree of this synthesis algorithm, they capture this highlight structure, so that something beyond this and this level, there's some information about the highlights are represented. So that the other approach is to challenge this one is like the deep learning synthesis thing. They're using machine learning as a tool, and so we hope to make an artificial network that work like humans and try to retune the internal representation as similar as possible. And this is very challenging, but many neuroscientists are interested in making this kind of model and to understand the human visual processing or animal visual processing or brain working. But important point is that what's the features, and machine can learn can do some task, and they are sensitive to a kind of features. But this is very simple picture. But of course what is learned by machine depends on the image database. So that we hope to use the database as big as possible that can affect the natural near all the natural images, and also we know that some adversarial example case some network is very sensitive to the noise, because those kind of systems become very sensitive to the very tiny features that works in a clear image, but doesn't work for the noisy situation. So probably this is the core of the features that can learn from this network, the machine network, and humans. And problem is that some are human interpretable, and others are not interpretable. And where the humans features are, I don't. This is just my intuition. And but probably this range, some of them are interpretable and machine learnable, but some are not, something like that. And this is the range where the current machine learning technique can cover. Of course, a development of the machine learning can go beyond this range. And the other thing we have to consider is how complex is the representation in the brain. For example, intrinsic image decomposition to decompose the image into the variety of, like a reflectance image or specular, or whether we really have this kind of separate representation in the brain is debatable issues. But this is a recent challenge of Sawayama-san and Pascal to apply the multi-spectral image to have a kind of ground truth of intrinsic image decomposition. And also we are interested in the intrinsic flow decomposition. It's not the intensity, but also the motion flow should be decomposed into the variety of factors of the object motions, or if there's a water, reflection by the water. The actual optic flow is addition of the many factors. So that how much decomposition actually human visual system is doing is an interesting topic. And one attempt is now running with the Yang app, is that we see how reliably we can estimate the speed of the object despite difference in the material. And if the visual system is perfectly decomposed, the motion flow coming from the material component and the motion flow coming from the object, probably our estimation of the speed would be very precise. And but at this stage, only we can say is that there are some overestimation of the speed for some material like this object, and we are examining how much low-level motion flows can explain this. Another thing is that we need to understand the Shitsukan process or material perception. We need a variety of data across different conditions, different kind of age of people or children or animals or the cortical response. But the problem is that unlike classical psychophysics, where everyone uses gratings or Gabors, it's not easy to use the same stimulus. But in order to compare the data across different studies, it's important to use the common stimulus. So that this is an attempt by Sayama-san, and he's making these images using Mitsuba, and then his database. He collects data for the standard human subject at the lab and also over the internet. And then this is now used by the variety of study in the DNA or the animal studies or the brain injured person or MRI study or so on. Okay, this is the end of my talk. Thanks.
Okay. Are there any comments or questions?
So how important is it to know for sure what the nervous system is encoding? Because those of us who work on it have trouble even defining what's being encoded in the nervous system.
Yeah, exactly.
And so it seems to me the comparison to the human psychophysics is kind of a moving target until such a time as we...
So I think the classical happy days where the features and the neurons one-to-one correspondence is gone, and many attempts have shown that the computational efficient but the complicated neurons is represented, just like probably today's talk by Professor Craig may relate it. But at the same time, psychophysics part, I wonder how much we can learn from the actual neural response itself at this stage. Probably we first return to the computation. Yeah, everyone has to consider what's the computation we actually do, so that then we can consider how that is represented in the neurons. So that I think the first role of a psychophysicist is to understand what computational information we actually use, and then consider how it can be represented, and I understand your point. But
when I talk this afternoon, the same thing will come up.
Yeah.
Other questions? Oh, can I? Oh, sorry. Please.
Thank you. So I was wondering, in the work on the order of the shading gradients, have you tried to apply this to more shiny objects, like nearly metallic objects, and to which extent does it work or fail?
So the reflected pattern itself has a very complicated order structure. So the one way is to do it is just cut some component that's higher than some if we can separate the purely specular reflected pattern from the more shading component, or it may work. So that at least Sawayama-san has tried to cut on some in a high intensity level, and then compare the MAL database. Luminance order is nearly the same. But of course, if you look at very high intensity zone, that reflects what's the environment structure is like. So that we believe that shape system has to ignore they have to look at how it is deformed. And of course, the type of information may change. And it could be for specular purpose, the second order structure should be seen. But at this stage, we just cut that component and compare it. Yeah, thank you very much.
Any short questions? All right. Okay, thank you very much.